All right, in our last section in chapter 10, we talked about multiplying radicals. Now let's talk about dividing radicals. And just like there was a rule with multiplication, where as long as my radicals were the same, I could combine them into one radicand, or if they were one radicand, I can separate them into two different radicals. It works the same way with division. We have a quotient rule for radicals that say, as long as the radicals are both underneath the same radical, we can separate them into individual radicals or combine them into one. We can use that rule back and forth. Let me show you some examples of how it might work. It says here in example 1, simplify by taking the roots of the numerator and the denominator. So you see in example number 1a, we have the cube root of 125 divided by 8. Well, if I were trying to do 125 divided by 8 first, it doesn't quite go in evenly. So instead of doing that, what I can do is use the rule that instead of taking one big fat radical, I can take two smaller radicals. I can radicalize the numerator and radicalize the denominator. I can do the cube root of 125 divided by the cube root of 8. It might be a little bit easier now to simplify because I know that there's a cube root of 25, 5, and there's a cube root of 8, 2. So I can really say that the cube root of 125 over 8 is really 5 halves. Look at B. I have the square root of 144 over p squared. We obviously can't take a 144 and divide it by p squared. But what we can do is separate it into two separate radicals. I have the square root of 144 over the square root of p squared. What number multiplied by itself gives us 144? 12. And we have two p's, so we can bring out a group. So we have 12 over p. And if you noticed up above, it told us that we don't have to worry about negative quantities, so we don't have to worry about absolute values here on our denominator on this one. Let's do another example. Example number 2, simplify. 16 x cubed over y to the 8th. No like bases here, no like terms, so I can't combine anything. But what I can do is try to simplify by separating my roots into the numerator and denominator. I can do the square root of 16x cubed over the square root of y to the 8th. Now I can look at each piece separately. Looking at the top, the numerator, the square root of 16 is 4. And how many x's do I have underneath? 3 of them, right? If I'm looking for groups of 2, it looks like I can bring out one group of 2, then I would have a lonely x on the inside. In my denominator, I have 8 y's. If I'm looking for groups of 2, what's 8 divided by 2? Or how many groups of 2 can I bring out? It looks like I can bring out 4 groups, and I have no lonely y's. So my final answer would be 4x times the square root of x all over y to the 4th. No like term still, but at least it's now simplified. Look at B. I have the cube root of 27 y to the 14th over 8x cubed. Nothing that I can do inside that radical. But what I can do is separate them into smaller radicals. I have the cube root of the numerator and the cube root of the denominator. Now let's try to see if we can simplify each piece. I'm going to start at the denominator this time. The cube root of 8 is 2, and if I have 3 x's, I can bring out a whole group and really say that I have a 2x in my denominator. Perfect. All right, let's look at the numerator. What's the cube root of 27? 3, right? And if I have 14 y's, but I'm looking for groups of 3, how many groups of 3 can you take? Well, it looks like you can take 4 groups, but then there would be 2 lonely y's left over. So my numerator would be 3y to the 4th times the cube root of y squared all over 2x. Again, no like terms, but I've simplified this radical.